Okay. Okay, so what the first thing I want to do? Let me just wait a second. How do I get this to? Oh well. Okay, so the first thing I want to do is go over kind of quickly just a couple points, high points from the last talk, the last lecture, the one about linear algebra, just in order to, because this corresponds to stuff that I actually want to talk about today, and then I'll get started on the topic for today, which is the algebras. So so last time the thing that I wanted to kind of go over last time was that from the linear algebra was the definition of what do you call it? O of n, which was the orthogonal group in n dimensions, and this is the this is just the group of linear transformations that preserve a kind of standard inner product, and more concretely, you could show that this actually corresponds to matrices M, such that the transpose of M is the inverse. That turns out to be the condition for preserving the inner product. And then one thing that we showed, if you satisfy this condition, then you have that the determinant of M is plus or minus 1. Okay. And then what I wanted to So then I think in one of your problem sets, what you had to show was that another characterization that this condition corresponds to the condition that all of the rows or all of the rows are orthonormal vectors in Rn, or all of the columns are orthonormal vectors. So you could also another way of thinking about this is that it's the set of all, since it's a collection of columns or a collection of rows, each of which are length 1 and orthogonal to all the others. You can think of this as the set of all orthonormal bases. It's another way of thinking of what the orthogonal group is. And then, if you like, one way of thinking about it as what the group element is if you take it's the group element that takes you from the standard basis to some arbitrary orthonormal basis. Okay, now just another reason for saying something about this is just to give you some kind of feel for what these sets look like. So it's a set of all orthonormal bases, and one way to get such a basis. Well, how do you produce all these bases? Well, what you do is you first the first thing to do is first you choose an arbitrary or a unit vector. So if you want to produce a basis, you have to produce a sequence of orthonormal vectors. So you start by just taking an arbitrary one of length 1. And so this is an element of the, so this is just an arbitrary unit vector in Rn. So I write it this way. It's an element of the n-1 sphere. So it's in the sphere of dimensions n-1, or the unit vectors in Rn. Then the next thing you do is choose. So you want to choose a vector that's orthogonal to this one, and also a unit vector. But you can think of what you're doing here is that you've picked some vector in the sphere here. Now, if you want to pick a second vector, which is going to be orthogonal to this vector, it's going to lie somewhere on on the equator. So you want to choose a vector on the equator. which is a S n minus 2. So it's a sphere of dimension 1 less. So this is your S n minus 1. Here is your S n minus 2. This is just the, and so this is the picture in f for n is equal to 3, but you can imagine this in higher dimensions. And then you kind of keep going until your last choice. Once you've got n minus 1 vectors, you're going to be forced which direction to go in the last choice. It's going to be in some sense the 0 sphere, which has 2 choices, either plus 1, either one direction or the other. And so then you choose a last one. So it has there's a choice of plus or minus. Yeah, so in 3 dimensions, your third choice would be either this way or this way. You have one choice, and then the plus and depending which one you choose, you're going to either get an oriented basis, a basis with a standard orientation, or a basis with the opposite orientation. If you put both possibilities together, you get ON, and then SON will be the oriented bases. This corresponds to what happens if you pick. Yeah, and this will correspond to picking the one which gives you a determinant of plus 1. Anyway, so this is what happens. So now, maybe I won't write the rest of what I was going to say. So you can think. Actually, maybe let me just say this. Write this up here, and then. So you might think. That ON is really the space. It's a choice of something on the n minus 1 sphere, and then a choice of something on the n minus 2 sphere, etc., and then down to S0, which is just Z2 plus or minus 1. So you might think that the orthogonal group is just this nice product of spaces, one for each of these choices, but the problem is. So this is not true, since each choice depends on the previous one. I mean, the problem here is that this equator here, where we had to choose a second vector in the equator, that equator depends upon our first choice. That's the equator of things that are perpendicular to the first choice. So what you've got is not a product of independent spaces, but you've got a product of points in these spaces where, what this space is depends upon where you are here. And so this is something that's called mathematics called a fiber bundle. Or it's also sometimes called a twisted product. So it's a twisted product. But it's quite a topologically subtle gadget. That's just the point. So the bottom line here is more not that I want to kind of tell you to get you all familiar with what orthogonal groups look like in arbitrary dimensions, but just to give you some feel for the fact that it's actually a very non-trivial problem. Even what the set looks like topologically is actually quite subtle. It's kind of a bunch of spheres, but they're kind of twisted over each other in a fairly complicated way. So that just even understanding any of the basic facts about the space is kind of a difficult problem in mathematics that kind of kept people busy a lot through the 1950s. Okay, so that's anyways, that's yeah. Okay.
Can we express these like just the purely algebraic information about O of n? Can we express in terms of an like an iterated semi-direct product in this way?
No, I mean, yeah. So there isn't. Okay. So one thing about this product here, this is purely. This has nothing to do with the group law. That, you know, when I made these choices here, when I started breaking it up this way, I really kind of I've seriously kind of wrecked the group law. So this is not a product. Yeah, so okay, remember, one thing to remember is the spheres are not groups. Okay, except, well, actually, sorry. So the S1, the circle, and S3 are groups, but in general, spheres, there is no way to put a group law on the sphere. So this is a product of spaces which are not groups. This is not a product of. This is not in any sense. There is such a thing as a twisted product of groups, which is what I think you're thinking of. But that's not what this is. These are not. This is not a decomposition into subgroups. Okay.
Well, thank you.
Okay. What else do I want to tell you about this? Okay, and then the but anyway, that's just to give you some feel for this thing. And then the other thing. So we had UN, and that was the matrices M, such that the M dagger, an adjoint, which is M transpose conjugate, that's the inverse. And this was the condition for this was the condition that this preserved the Hermitian inner product. And again, each of the rows and columns of this are going to be sets of complex vectors which are orthonormal with respect to the Hermitian inner product. And this one, the condition, there isn't and this one, the condition was that the determinant is an element of U1. So in other words, it's going to be equal to e to the I theta for some angle. So in the case of the orthogonal group, the determinant was just this kind of thing that was either +1 if you're in the component of the identity, or it's -1 if you're in the other component, which in some sense you should think of as being the the orthonormal bases with the opposite orientation. Here, in UN, the determinant actually isn't just +or -1. It's an arbitrary number, a complex number of unit length, and so it's a more interesting piece of information. But generally, what we're going to do is we're going to generally kind of treat it separately and restrict attention to so SUN, which is the subgroup with determinant equal to 1. So if we so often what we're going to do is just go to this case, and it's not that there's not potentially something quite interesting about the extra piece of information in UN. It's just that it's generally a good idea to treat it separately, otherwise it gets confusing. Okay, so that was the story from last time, I think, that I wanted to say. But are there any questions? Any questions about this stuff? I mean, this is meant to be fairly straightforward. Okay. Oh, and then you can then, if you think a little bit, you can also, if you play around, you can also see that there's a similar argument to what I did here. If you look at, these are a bunch of complex vectors orthonormal with respect to the Hermitian inner product. You find out that these guys are twisted. These guys are also twisted products of spheres, except they're twisted products of odd dimensional spheres. You can work that out. But it's the same story, that these are actually these groups kind of get very, very complicated to understand very quickly. And in practice, what's going to happen is that we're going to talk about a lot about SU2 and a lot about U2, but we're rarely, if ever, going to actually talk about even the next step up, which is SU3. SU3 is an 8-dimensional space. It's you can think of it as a twisted product of 3 spheres over a 5 sphere, and it's got all sorts of complicated things going on, and often a course like this will kind of go in the direction of spending a lot of time trying to get you to understand what's going on with SU3. But we're gonna head off mostly in another dimension, in another direction. But this is just so this is kind of, in some sense, all you're going to hear about in this course mostly is, very low dimensional cases, O3, O4, SU2, and then we'll do a lot of things which apply for arbitrary n. But I won't go through the technology to deal. If you really were asked a question about SU3 or SU4, what the technology is that you would have to deal with it. Okay, so what we're going to do today, though, is get to the main kind of the main piece of technology that you do use to work with these things, which is the notion of a Lie algebra. And let me actually, so the warning about this chapter is it's like we're kind of been alternating between a lot of heavy duty, abstract, powerful technology and some simple examples. And now this chapter, we're back to heavy duty technology for this chapter. And I want to, but what I want to do is maybe I'm going to start by just kind of outlining what the kind of very, very abstract point of view about this is, and then kind of start to work our way down to actually, working out how to actually do calculations for this stuff and how to use this more practically. Okay, so let's see. So so let's go to, so this is the, and one last thing also to say about this chapter, there's some things in here. So you may find that this chapter is really a bit too much to deal with at this point. So one recommendation is you might kind of get as much of it out of it as you can now, and then kind of come back to it later as you see more examples. And in particular, the last section, there's a section about complexification, and I'll explain why that's there. But that's an extremely confusing point, and I put the section there just because it fits naturally there. But it's probably not a good idea to spend your time now thinking about that confusing point until it comes up later in the class. Okay, so here's the. Okay, so let me give you the highly abstract point of view. If you know. Okay, now what we've been talking about is Lie groups, and as and these are basically sets with a multiplication on them. And if you know about and there are things like, for instance, if you get to SU2, it's a 3-dimensional sphere. So you can think of these as being some nice, very kind of symmetric gadgets, but let's call it G. But they've got a distinguished point, which is the identity. Okay. And then we've got a representation, which is a map that takes elements in here, takes G here to some standard matrix group, glnc. So just to invertible matrices, and that's, as I've been kind of trying to say, that this is, as you go to larger n, these things get more and more complicated. It's a very complicated space in some sense. Though glnc, well, anyway, so it's better probably not to try to think too hard, what glnc looks like as a manifold, as a space now, but it's just some space, and again it has a distinguished point, the identity. Okay, and now so then pi is just some map that takes you from here to here, pi. So this is G, pi of G. So this is just some invertible matrix. Okay, now it turns out that the way to really, so this is a horrible kind of nonlinear problem. This is a really complicated nonlinear space. This is a complicated nonlinear space. You can't add these things and get a third one. You could, and this is very tightly constrained map from this nonlinear space to this nonlinear space. Now, so that's a very hard thing to kind of work with. So what we want to do is we want to we want to do a kind of standard thing, which is given something nonlinear, find a linear approximation to it. So linearize it. And so first we want to linearize these two spaces. We want to get a linear approximation to them. And so what you do is you take the tangent space at the identity, and I'll say more about what that is. At the identity, and then you take the tangent space at the identity here, and what you're going to do then is you give this linear approximation to the group is what you call the Lie algebra, the G. All right. So sometimes what I've been doing in the books, I've often been using this convention among mathematicians, which is to use the German Fraktur font. So the Fraktur G will be but since I have trouble writing those on the blackboard, I'll often just write Lie in front of this. And so this is a vector space. This G itself is some nonlinear thing. Lie G is just a vector space of the dimension of G. And over here, it's going to turn out that I'll show more about this later. That this is the Lie algebra of glnc. But it's going to be the same thing as all the n by n C matrices. Okay. So the tangent space here. Space at the identity is the Lie algebra over here. Okay, and now what we're going to so the first thing that we're going to do today is kind of tell you is kind of to talk about these tangent spaces and to try to tell you something about how to understand these tangent spaces and what they look like for a Lie group, and then what we're going to do is ask the question, if you're given a representation, if you're given one of these maps, how much of the information about this map is carried by just looking at what happens near the identity. So this is the kind of piece of really abstract nonsense which you see if you take a class on the theory of manifolds, is that if you have a nonlinear mapping like this between two nonlinear spaces, you can take its derivative. And if you take its derivative will be a linear map from the linearization here to the linearization here. Okay, so pi has a derivative. And I'll just call it pi prime. Pi prime, and pi prime. Let's take pi prime restricted to the identity, restricted to the 1. Well, restrict. Yeah. Let me just say anyway. Pi prime just takes tangent spaces to tangent spaces. In particular, you can look at the identity, and it's gonna be a linear map. From Lie G to Lie glnc. Okay. Okay. So the idea of the Lie algebra construction, from how it's related to what we've been doing in terms of Lie groups, is that it's just it's really just going from the whole group to just the tangent space at the identity, and then any representation just go to the linear map that you get between these spaces. And the point is that this is a whole very nonlinear situation, very hard to kind of work to do things with. This here is just this is a vector space. This is a vector space. It's actually just the vector space of these matrices, and the derivative of your representation is just a linear map between vector spaces. Okay, it's something that if you feed it some x, some element of lead g, it goes to pi prime of x, and pi prime of x is just an n by n matrix. Okay, so this is just a linear. So pi prime is just a linear map from this vector space to this vector space. And so in principle, everything then comes down to linear algebra. So this is the abstract nonsense. And now somehow the point is that the fact that this is a homomorphism. So this implies it's going to imply this. So this is one of the main things I want to show today, is that if the fact that this is a homomorphism implies that these linear maps have this property, that if you take the that you can take actually the problem I guess I have to anyway. Let me leave this for later, and I guess I have to say this a little bit later. Anyway, let me say this. Let me kind of tell you what this is later, because I can't quite state it now without defining something else. So this is kind of the question I'll leave hanging, is that okay, this whole story is about linearization, and if you linearize, then the only the funny thing about these maps are that they're homomorphisms. So what piece of it? What is then the funny thing about this? The big constraint that you get on these maps. Okay. So anyway, so this is just at this point just the kind of abstract nonsense. And what I'm going to do now is going to start work my way down, and to try to kind of explain how to how to kind of realize this kind of grandiose picture in a much more concrete way. Okay. Okay. So let me just get rid of this. Okay. Okay. So so there's kind of a trick here, is that it turns out that we'll restrict attention to matrix groups, to G matrix group. So what this means is so all the groups that we've seen so far, things like UN and ON, they were all defined by saying, elements of the group are given by matrices, and by a matrices satisfying some condition. So that's going to be the groups that we're actually going to look at. And the weird thing about this whole theory is that there's a very small number of examples of interesting Lie groups that are not matrix groups. There exists very few interesting G that are not matrix groups. Yep. And often when we teach the course like this for graduate students in the math department, what we just do is we just say, okay, well, we're dealing with these because the the small number of examples that aren't of this form are actually just really not interesting, and we'd rather not talk about them. And let's go on. But the problem is that this actually is going to come up in the course. This actually comes up in an interesting way in physics. One does appear in quantum mechanics, and we'll discuss it when we get to it. It's called the Metaphytic Group. Okay. So it's a so there's actually an argument that if you really want to understand everything we're doing in this course kind of rigorously, we shouldn't just restrict to matrix groups. We should really work with all possible groups, because we're going to hit one which isn't defined in terms of matrices. But the problem is that if you try and teach a course like this without restricting to work with matrix groups, the technology becomes kind of very complicated. You have to deal with kind of serious technology manifolds and anyway, and I don't want to get into that. So we're gonna say that we're gonna assume for now that all our groups are matrix groups, and then just at some point in the course, I'm going to point out that here's one that just appeared, which actually isn't a matrix group. And, but there's kind of in some sense only one that's interesting in this case. Okay, so if we got a matrix group, then what we can do is we can then define the algebra in a much more in a much more concrete way than just as this tangent space. And so let's say I want to do it. How do I do this here? Okay. So here's the definition that we're going to use. So here's the definition. It's that so this is for a matrix group. So Lie algebra is so this means that G is some group of invertible n by n matrices. And what you want to do, the algebra of G. So let's just say it this way. So Lie G is the set of space of n by n. Which way I want to do this? N by n matrices. Use X such that e to the Tx is an element of G. Okay. So we're going to now, so now all of a sudden, instead of thinking of the Lie algebra as this tangent space, this abstract geometrical gadget, I'm now going to say, okay, well, our groups are actually something much more specific. They're groups of n by n matrices, and once we've got n by n matrices, I can in some sense say, well, the Lie algebra is kind of, in some sense, kind of the log. These are things that are in the log of the log of what we get when you take a groups, and so that they're but a better way to say that is that there are things that there are matrices that you can exponentiate, perhaps with this parameter, and get elements in the group. Okay. And what so this is a much more concrete thing. So you can, exponentiating matrices, remember, so e to the tx is just, the identity matrix plus t times x plus t squared over 2 factorial x squared plus, it's really just this. And you can see that, the exponential is something which has an infinite radius of convergence, where you can show that, certainly for x small enough, this is gonna converge. Okay, let's see what else I want to tell you about this. Now, so the connection Now, so this is the very kind of concrete way of thinking about it. Let me kind of go back just a minute and give you the connection to the abstract nonsense. And so so the relation to the definition as a tangent space. Well, so if you've seen if you take a course in geometry, differential geometry, at some point one of the main problems that the course hits is how are you going to define, I mean, almost by definition, a manifold is something which locally looks like Rn, and so has a well-defined tangent space, but how are you going to define the tangent space of a manifold? And so one definition of a tangent space well, you've got some arbitrary curved manifold, and you've got this tangent space at a point. What you do is you look at all you look at all curves in the space going through this point. So all kind of curves that do this or this. You look at all curves. Sorry, they better stay in the manifold. And then the way you define the tangent space is by so the space of velocity vectors of curves, tangent space at a point, curves through the point. Okay, so here there's some trickiness you have to go through to actually make this a well-defined. You have to say exactly what you mean by velocity vector, or what you mean when two curves have the same velocity vector. But once you go through that, then this tangent space can be thought of. Elements of the tangent space can be just thought of as possible velocity vectors of curves to the point. And so what we do here, so here for us, if the e to the tx is a curve in G that goes through the identity point at t is equal to 0. Okay, if you put 0 in here, you just get e to the 0 is 1. So in our case here, and this is our space, for G, then these tx's that we've constructed, these are curves. They're very very special curves. So they're not things that do something arbitrarily complicated, but they definitely go through this point. They kind of come back out here, and they have a velocity vector at 1. Okay. And if you take the derivative, if you ask for the velocity vector at 1 is the ddt of e to the tx at t is equal to 0. T is equal to 0 is when you're at 1. But if you take the derivative with respect to t of this matrix, it's e to a parameter times a matrix. What you're going to get is just I mean, taking the derivative is just going to pull down a factor of x, and so you're going to get x e to the tx at t is equal to 0. Right? But this is then what? But this is just x. Okay, so you can think so the relationship between this definition, the definition of x's as the things where you could exponentiate that like this and get group elements, and the definition of the tangent space of the group at the identity is works out very nicely if you define your tangent space as a space of velocity vectors and velocity vectors of curves. Well, this guy is the velocity vector at t is equal to 0 of this curve. Okay, so this is just an explanation between what we're going to work with, which is these guys, which are very, very concrete things, and then this kind of abstract nonsense that I was trying to sell you on at the beginning of the class. And it's mainly perhaps useful if you've had some manifold theory, but you can see the kind of anyway. We're going to do a lot of calculations when we're working with a Lie algebra element x. Often we're going to work with it by exponentiating it and looking at it as giving us a curve in the group, and then seeing what happens to those curves, in a linear approximation near the identity.
Professor?
Yeah.
Is it possible to put all matrix groups in the form of this exponential? E to the tx for some x?
Yeah. Well, this by definition is the well, you can. Okay. Okay. So the point is that this is true near the identity. Okay. So this is telling you about yeah. So I mean the logic of this is kind of is being done a little bit carefully to not get into possible sorts of trouble. And let me maybe just say some words about it. One is that, so I mean, if you look at the way I've worded the definition, is that the Lie algebra is the stuff that when you exponentiate it, you get elements of the group. You get elements of the group. Now, I haven't said that you can get any element of the group by exponential. I mean, I haven't said that this is surjective. I haven't said that you can get any group element you want by doing this. It's true near the identity. It's true that you can do, because these guys are the tangent space of the identity. So it's true. It turns out that near the identity you can get anything in a neighborhood of the identity of the group by exponentiating a Lie algebra element. But the definition just says that if you exponentiate these, you'll stay in the group. It doesn't say that you'll hit the whole group. Okay.
As long as the group is compact group, you can do this, right? Something like UN or SON.
Yeah. I mean, yeah. So and I think in one of your problems, was it the problem for this week, or I think for this week, yeah, you see that if you do non-compact groups like SL2R and SL2C, there is a problem with this. But there is compact groups. Yeah. Anyway, I really want to avoid getting into the general.
Compact groups, these guys each to the power tx is a geodesic polynomial.
Is it what?
Is a geodesic polynomial.
A geodesic. Yeah. Anyway, I don't want to. Anyway, I don't want to get into the general theory. I want to kind of specifically stick to. Yeah, I mean the definition that this definition of a Lie algebra is especially chosen to avoid a host of kind of really complicated issues about the global behavior of Lie groups. And so I want to, but the Lie algebra really it's something that just knows about what's happening near the identity, and and that's all. And all I want to, the only thing that's in the definition says that X is a matrix that if you if you compute the exponential of that matrix, you will get a matrix element that's in the group. Okay, that's all. But yeah, I want to avoid the general theory about what. Okay. Any other questions about this? Okay, so let's now see what I've got. Okay, so let's get back to the let's get back to these examples that I started with from last week, the unitary and orthogonal groups. So in the let's work out what happens for these. Okay, so let me first say one thing to say, which I won't try to prove, but it's fairly easy to see, is that if you take, if you ask, what are the things that when you exponentiate them, you get an arbitrary invertible matrix? Well, it's basically any matrix. So the Lie algebra of gln, either R or C is the n by n matrices, R or C. Okay. So the really simple Lie algebras are those of the group of invertible matrices, because basically if you take any matrix, exponentiate it, you'll get an invertible matrix. You'll get one of these, and so you get anyway. So these Lie algebras are very simple. But now your problem is, what if you've got some kind of subgroup of this? You've got some kind of group of matrices which are satisfy some kind of condition. Then what's the condition that these X be in the Lie algebra? And so let me just say this very quickly. So we have the condition for O of n or U of n. One way of saying it was that if the group element, well, let me say this, I guess G times G adjoint is equal to the identity. Okay, in both cases, and here by if you're in UN, this is the transpose conjugate. If you're in ON, it's just the transpose. But you've got this. This is the condition. So then what we want to do. So this implies that well, so since this implies that e to the t x t x. So if G is of the form e to the tx, then you have e to the tx and then e to the tx, and then your adjoint is going to be equal to 1. But if you take the exponential, the way adjoints work, this is the same thing as e to the tx, e to the tx adjoint. I mean, if you take the adjoint of a product, you get the product of the adjoint. So the way so this goes to here. And then now what you want to do is differentiate this equation. So take ddt of this at t is equal to 0. And then what you're going to get is you're going to get e to the tx. So you get e to the tx, and then so then it's a product rule. You're taking this times the derivative of this plus this times the derivative of this. So this times the derivative of this is e to the tx t Then there's an x dagger, e to the t x dagger, and then this. Sorry, I really should. I got to make my daggers look different than t's. Sorry about this. Plus derivative of this times this. There's an x e to the tx. E to the tx dagger. This is equal to 0. Okay, now these guys, this commutes with this, so you end up with a, anyway, so maybe it's better to say evaluate at t is equal to 0. At t is equal to 0, you get, everything becomes 1 except this, and you get x dagger plus x is equal to 0. And so for ON, this is that the x transpose is equal to minus x transpose plus x equal to 0. And for UN, it's x dagger is minus x. And this is what I sometimes call this. So these matrices are sometimes called antisymmetric. You take the transpose, you get a minus sign. These are sometimes called skew. Sometimes called skew adjoint. So I mean, being self-adjoint is when you take the dagger, you take the adjoint, and you get back the same thing. Well, if you get a minus thing, we call it skew adjoint. And so I should say that we've already seen you've already seen some examples of this. One example you saw here was already when we did SU2. Remember, I showed that there were these when I defined the x of j is equal to minus I sigma j over 2. And then I showed that these things had satisfied some nice commutation relations. Well, these are a basis for the Lie algebra of SU2. Okay. And so the sigma matrices that physicists like to work with are kind of a basis for the self-adjoint 2x2 matrices, but we'd like to put in this minus I in order so that they have this property, and then with the minus I they're skew adjoint, and they form a basis for the Lie algebra. And we'll see in a minute anyway, the 2 is the normalization that makes the commutator work out well. Okay, so this is the.
Could you explain again why the Lie of the general linear group is just the general n by n matrices? I just didn't.
I didn't really tell you that. I'm trying to think about what's the best way to say that. I mean, the thing is really that we want to. Yeah, I'm sorry. I hadn't thought about what the best argument for that is. I mean, it's certainly true. I think maybe the argument is just that you can see that if you take an arbitrary matrix. Okay, let me say something about more about that. But anyway, okay, but this is the story for the for these subgroups. Let's go back to GLN R or GLN C. It's the same thing. Let's see. So how do you have to argue? Okay, so one. Okay, so if M is just some matrix in n by n matrix in either R or C, it's the same story. Now, if you take e to the t sorry, let me just call it x, I guess. Okay. So if you take e to the tx, this is going to be, well, you have to worry about convergence of this, but as I said, I mean, you can look at the power series for the exponential has these factorials in it, which causes these things to have an infinite radius of convergence. So then what you do, but then this guy, is invertible. So, with inverse, which is e to the minus tx. Okay, and you can see that if you multiply this guy by this guy, because x commutes, you have to worry when you're what the properties of exponentials are going to be if you multiply two exponentials with different matrices. But it's the same matrix, so they're just gonna cancel, and you're gonna, this times this is going to be the identity, right? Okay, so we've shown that this guy, has this property that if you exponentiate these guys, you get invertible matrices. And I guess maybe that's all. Maybe that's actually all I need to say is that it's in my definition of what the algebra is, it's fine. It's just that this is a I'm worried now that I missed something in this definition that you have to worry about whether are you only getting a subspace. But you can show. But the other thing you might want to show is that near the identity, near one, any element of gln for R or C is of the form approximately the identity matrix plus some small number times x. I guess the point is just that the dimension of this thing, the dimension of these guys, this has dimension n squared, and this guy also has dimension n squared. So it's the same. Anyway, it's the same. You're surjective near the identity matrices. Does that help? That's about as much as I want to say now, I think.
Yeah, that clears it up.
Yeah, but I kind of skipped over that. Okay. Any other questions about this stuff? Okay, so now let's get down to the next tricky part of it. I'm starting to run out of as much time. Okay, so one thing I recommend is there's a section 5.3 called a summary, and this is just kind of all the kind of facts about examples of Lie groups that we talked about before and examples of what their Lie algebras are. So this is kind of summarizes everything you should know about. Okay, now now I think, okay, so this I'm gonna have to do this a little bit quicker now. Okay, so now there's something which okay, so now the another interesting thing about the Lie algebra is that the Lie algebra automatically, the Lie algebra is a vector space on which the Lie group acts. So you have something called the adjoint representation. So the Lie algebra. So let's say this. The Lie algebra. So let's just say it this way: that G acts on VG. And let me, maybe I better write this down by conjugation. Where did I write this down? I'm doing this a little bit different order. So it's got so x. So let's take pi of g applied to x is g x G inverse. Okay, and you can check that if you if e to the tx is in a group, that if you take anyway that conjugating it by a group element doesn't change that property. Okay, and this is called the adjoint representation. The adjoint representation, and so we'll write it, and it's going to be, so we're going to write instead of pi, we're going to write big ad, and then the space that you're acting on is Lie G. Okay, so one part of the story is that any just from the definition, once we define the Lie algebra, the group acts on it in an interesting way, and all of a sudden we have a representation of the group. So this tells us that if anybody hands you a Lie group, you're automatically, from the definition, by looking at the action on the tangent space identity, you get an interesting representation called the adjoint representation. Okay. And then this is now the so here's the warning about is that these groups that we're talking about are real manifolds, and the tangent spaces to them are real vector spaces. For instance, SU2 is a three-dimensional space. It's got a three-dimensional tangent space that you can't make 3 dimensions out of pairs of out of complex numbers. It's got the wrong dimensionality. So you've got so warning is that this is a real representation. So we want to complexify it. And basically, when you complexification, in some sense, wherever you see a real number, you're allowed to throw in a complex number. But to make things just totally horribly confusing, this group, this may be a Lie algebra of matrices that are written in terms of complex numbers. So you have to think about what does it mean to complexify a group of complex numbers, and this is where things get truly horrible. And this is when we get to some examples of it, I'll say more about it. But right now, this is just a warning for now.
So really quickly, Professor, you're saying that while there are complex numbers involved in these matrices, the scalar field is the real numbers until we complexify it.
Yeah. The elements of this are real linear combinations. Like for instance, for SU2, the Lie algebra of SU2 is real linear combinations of these x sub j that I wrote down. Okay. So if you take any complex linear combinations of the x sub j, you're going to get a different group. You're going to get SL2C. So that's the subtlety. But this really is this gets very hard to wrap your mind around. All I can say about this right now is that if you start thinking about this and you don't find it confusing, you're not understanding the problems. Okay. So anyway, but I'm not going to say any more about this now, except just to notice that the way we define this, we ended up with a real representation. But I told you at the beginning of the class that we want to do complex representations, and that we need to do complex representations. So you got to do something to this to make it work. Okay. Now let's see. So what did I want to do? Okay. Okay, so here we're going to get down to a crucial calculation. But first, let me give you the definition. So here, there's something special about these vector spaces, corresponding to the fact that they come from group elements which have this nice property that you can multiply them. So the question is kind of what corresponds to the fact that you've got a group law on e to the tx. Well, it turns out, and I'll show in a minute, is that the condition, the way you see the group law on the e to the tx is in terms of the commutator of the matrices in the Lie algebra. So let me give that a definition. Give a definition. So the Lie bracket operation on VG is the map well it's a bilinear map, and then or it's the thing that you feed this two vectors. So it's the thing that takes G G, and so X and Y goes to X, Y. So what this is, and this is just X, Y minus Y, X. Okay, so this is a nice thing about thinking about the algebra elements as matrices is that you can just this bracket operation is just given by taking the commutator of the matrices. But what do you have to show? So and sorry, this is going to be 2 Lie. Okay, so the point, the whole point here is that this is a bilinear operation that if you feed it two elements of the algebra, and you do this to it, and you get back another element of the algebra. So that's what you have, and that's not so obvious that that's going to work. I mean, you could take somebody gives you. I mean, it's clear it's going to work for glnc, because then it's just you take the commutator of any matrices, you get a matrix. But it's not if you take two self-adjoint gadgets, you have to worry about take two skew adjoint gadgets. If I do this, is it still going to be a skew adjoint? You have to worry about that in general. And the general maybe let me give you a quick argument, because it's an important computation that explains why this guy has to be in the Lie group, in the Lie algebra is this. Let's see. Okay, so it's this. So what you do is you take. Well, you can take the adjoint. You take the adjoint You take the adjoint action of e to the tx on y. So x. This is x, y are in the Lie algebra. They're things that if you exponentiate them, you get something in the Lie group. Well, remember, so this guy is then, e to the tx, y, e to the minus tx. Right. And you know that he's anyway. So you know that he's in the Lie algebra. You just because this is a representation anyway. You could. But that's a different argument. And then what I want to do is to show is that if you take, this is for any t, and this implies that this is that the derivative, the velocity vector, there is also. Okay. So this guy, as you vary t, he's moving around in the Lie algebra. But if you've got a path that's staying in this nice vector space, and if you take the velocity vector of that path, it's got to stay in here too. So that implies that the EDT of e to the tx y e to the minus tx is in Lie G. And then now I won't do the computation. It's in the notes. But if you do this computation again, just use the product rule and keep track of what's going on. And what you'll find, so you evaluate this set, evaluate Okay, let me say. So you get that ddt of e to the tx y e to the minus tx evaluated at x equal to 0 is the commutator of these guys. So if you just compute this out, and you get two terms using the product rule, and then they t is equal to 0. Equal to 0. And then put t is equal to 0 in the two terms, and you'll just get xy minus yx. Okay, and so this tells us then that this guy is in that if we take every two x and y that are in the Lie algebra, if we take the commutator of the matrices, it's still in the Lie algebra. But so that's one use of this. But I think I also want to this formula is going to be very, very useful, because we're often going to see these commutators appearing, and they're going to have some interesting properties. And to understand why they have that interesting property is that this is really kind of this is what you get when you act kind of infinitesimally near t is equal to 0 by if you conjugate this guy by the exponential of this guy, you get this commutator. So you should sometimes think, instead of just thinking of this as a product, as a difference between these two products, it's often a good idea to think of it this way. And so I want to just kind of remember this formula. We're going to find it very, very useful as we go on. Okay, so now let me just kind of finish up by telling you the last. Let me go back to what I did right at the beginning, and I told you that a Lie algebra representation was a representation was a homomorphism from G to glnc. Well, that what we were interested in was the derivative, and the derivative was going to be a linear map from the Lie G to Lie glnc, which was the matrices. So let's go now. Let's say this much more concretely in terms of all this stuff, and this is where you have to use. You're going to have to use this formula to show that this has the right properties. But I think what I'm going to do now is just give you the definition and then leave you to check the properties. So here's the definition, and this is kind of. So these, in some sense, are the main objects that we're going to be interested in throughout the course. So a Lie algebra representation of Lie algebra Lie G. Lie G. It's going to be so again, it's going to be let me call it a, do I give it a name here, a phi, on a vector, and again, everything, we're going to do everything over the complexes. Our representations are all complex on a complex vector space. V is given a linear map and let me call it, I guess I should call it this and then put the V in here. It's given by a linear map phi that takes x in the Lie algebra of G to phi of x. So that's an element of the Lie algebra of glnc, which is the matrices, such that 5x of phi of xy. Okay. Okay, so this is kind of what I was trying to say at the beginning, was that these, if somebody hands you a representation of a Lie group, G, what you can do is you can take the derivative, and then the derivative will be a map from the tangent space to G to the tangent space of GLN at the identity, which means it'll just be a linear map between these vector spaces. But it has to have a certain property, and I wrote down a question mark at the beginning of that what that property was going to be, and this is what it is. So you could think of it as that maybe in words is that phi preserves the Lie bracket. If you want to, in other words, so you take the bracket of a phi is phi of a bracket. So this is kind of the right homomorphism property for Lie algebras for this algebraic operation. Okay, and then maybe just one last thing to say is that this is unitary. So phi is unitary. If phi 5x dagger is minus 5x. Okay. So if this guy takes you to not just to glnc but to the unitary matrices, then it's going to be the phi of x's are going to be skew adjoint, and then you know that you have a unitary representation. So most of what so this is I'll kind of start here maybe at the next time, but this is kind of the kind of fundamental abstract gadget that we're actually going to work with. I started out by telling you about this fundamental abstract gadget of Lie algebra homomorphisms or representations, but really, and if somebody hands you one of those, you can take a derivative and get one of these. But what actually is going to happen more often is that you're not actually going to have the representation of the group. You're just going to have one of these, and this is actually what you're going to work with, and it's going to be these operators, these phi of x's. These are going to be the operators that occur in quantum mechanics, and that these are going to be your and they're going to be nice skew adjoint operators. They're going to in some sense be your interesting observables in quantum mechanics. Anyway, so let me stop there. And again, there are a few other interesting things in the chapter. You should look at those. Let me know if you have any questions about them next time. The main warning is about the last section about complexification. That what it means to complexify a space like a space that's already complex is very tricky, and I don't want to. When we actually do use that, I'll talk more about it. Okay. So any questions about any of this stuff? Okay. Anyway, so next time I promise you we're going to get back to much more concrete things. This is the end of a dose of kind of heavy duty abstraction and heavy duty mathematical machinery. But this is kind of the fundamental machine that we're going to be using through most of the course. So I wanted you to kind of see it in this abstract form, and then it'll start to make more sense as we work through examples of this. We'll work through different examples of the of representations and the algebras of the groups. Okay. So I'll shut this down. And again, if any of you want to hang around and you have any questions, start up. Just connect to the other Zoom section for this. Okay. Bye now.
Thank you.
Bye.
Thank you, Professor.
Bye.